Hello everyone, this is lecture 5 of the subject integrated circuits. In this lecture, I am going to discuss astable multivibrator using 555 timer IC. Contents are 555 timer IC. Firstly, I will give the description of 555 timer IC. What is this IC? Then pin diagram of 555 timer IC. After that, functional diagram of 555 timer IC. In this, I will explain the internal circuitry of 555 timer IC. Then we'll discuss about astable multivibrator using 555 timer IC. Then applications of astable multivibrator using 555 timer IC. So starting with 555 timer IC. So this is called 555 because this IC, it internally contains 3 5 kilo ohm resistors, and this 555 timer IC was first introduced by Signetics Corporation, and by Signetics Corporation this device was named as SENE 555, and it was come in early 1970. So this SE and NE series 555 timer IC is having different temperature range. For example, SE 555 is designed for the operating temperature range from -55 degree centigrade to plus 125 degree centigrade, while NE 555 IC, it operates over a temperature range of 0 to 70 degree centigrade. So both the series is having different operating temperature. So we use SE and NE as per the requirement of the application, right? So basically this 555 timer IC, it is a timing circuit. It is a timing circuit that can produce accurate and highly stable time delays or oscillation. So the main purpose of 555 timer IC is to provide delay and is to generate the oscillation. So we can say that this 555 timer IC, it works in two modes. In one mode, it is used to generate a duration, a pulse of a particular duration, that is the monostable mode, and in other mode it is used to generate oscillations, that is the astable mode, right? So I will discuss that the modes of 555 timer IC, but the main purpose of 555 timer IC, that is to produce accurate time delays and oscillation. And this 555 timer IC, it requires a supply voltage of +5 to +18 volt in both the free running and one shot mode. That free running, that is also called astable mode, and one shot mode, that is also called monostable mode. So this astable mode, in this astable mode, there is no stable state. There is no stable state. So the output keeps changing its state from low to high and high to low. That's why this astable mode, it is also referred as free running. And in astable mode, it does not require any input. So without any input, the output keeps changing its state, high to low, low to high, high to low, low to high. So 555 timer in astable mode, it generates a pulse of a particular frequency. That's why it is called free running. And in monostable mode, as the name suggests, mono means one. So in monostable mode, it is having only one stable state. That's why monostable mode is also called one shot mode. And 555 timer, it is having adjustable duty cycle. Just by changing the value of external resistor and capacitor, we can change the duty cycle, and the timings which is generated by a 555 timer IC, it ranges from microseconds to hours. And 555 timer IC, it can source or sink 200 milliampere current, and the advantages of 555 timer IC is it is reliable, easy to use and low cost. So these are the few specifications of 555 timer IC. So this 555 timer IC, it is It is a 8-pin IC. So we'll discuss about it. So coming to the modes of 555 timer IC. So 555 timer IC, as I discussed it, it operates in two modes. The first one is astable multivibrator and the second one is monostable multivibrator. This astable multivibrator, it is having no stable states. It is having no stable state. So in astable multivibrator, the output of the astable multivibrator, it keeps changing its state, that is from low to high, high to low, low to high, high to low. So we get a pulse waveform of a particular frequency from the output of a stable multivibrator, and the frequency of this pulse waveform, it depends upon the external resistors and capacitors. By changing the values of external resistor and capacitor, we can change the frequency of this pulse waveform. Also we can change the duty cycle, right? So this astable multivibrator we can design using operational amplifier, also using 741 IC. Also we can design it using 555 timer IC. Now coming to the monostable multivibrator. Monostable multivibrator is a multivibrator which is having one stable state. Mono means one, so it is having one stable state. So in 555 timer, let's say if the logic 0 state is the stable state, so when a trigger pulse is applied in the monostable multivibrator, then the output of the monostable multivibrator, it changes from logic 0 to logic 1, and it will be in logic 1 state for a particular duration of time. Let's say this time is t, and after completing this time t, the output will again come back to the logic 0 state, that is the stable state. So monostable multivibrator, it is used to generate a pulse of a particular duration, and the value of this t, it depends upon the value of the external resistor and capacitor that is connected in the circuit, right? So monostable multivibrator, it is used to generate a pulse of a particular duration, and monostable multivibrator, it requires a trigger pulse. It requires a trigger pulse, because when we apply the trigger pulse, only then the output of the monostable multivibrator will change its state from 0 to 1. Otherwise it will be in logic 0 state, it will be in low state only. So the difference between astable and monostable multivibrator is, the first difference is astable multivibrator is having no stable state, while monostable multivibrator is having one stable state. And in astable multivibrator, no input is required, no trigger pulse is required, but in monostable multivibrator, trigger pulse, input trigger pulse is required. So in this class we are focusing on astable multivibrator only, right? So coming to the pin diagram of 555 timer IC, as this 555 timer IC, it is a 8-pin IC. So firstly I am going to discuss these 8 pins. Pin number 1 is ground. So all the voltages in 555 timer IC circuits are taken with respect to this pin number 1, because pin number 1 is ground. If we compare this 741 IC with the 555 timer IC, then in 741 IC there is no ground pin, and in 741 IC there are two supplies required, plus VCC and minus VCC. But in 555 timer IC only one supply is required, that is the positive supply, that is the plus VCC, that is connected at pin number 8, right? Pin number 2 is the trigger. So this trigger pin is mainly used in monostable mode, because in astable mode no trigger pulse is required. So in astable mode we simply short this pin number 2 with pin number 6 in astable mode. But in monostable mode, since the trigger pulse is required, so that trigger pulse is applied at pin number 2. From pin number 3 we take the output. Pin number 4 is reset. So the function of reset is just to make the output 0. Basically this pin number 4 it is connected to the base of the PNP transistor, that I will discuss separately in the internal circuitry of 555 timer IC. So by applying a negative pulse on this pin number 4, we can reset the output. If we are not using reset pin, then we simply short this pin number 4 with pin number 8. Pin number 5 is the control voltage. If we want to change the width of the pulse generated by the 555 timer IC, so for that we can apply a voltage at pin number 5. Otherwise, we can change the width of the pulse just by changing the values of the external resistor and capacitor. Again, if we are not applying any voltage, if we are not using this pin number 5, so we simply connect a capacitor of 0.01 microfarad in between pin number 5 and pin number 1, just to remove the ripples and noise. Pin number 6, it is connected to the non-inverting terminal of the upper comparator. Since this 555 timer, it contains 2 comparators, and there is one upper comparator and lower comparator. So pin number 6 is connected to the non-inverting terminal of the upper comparator, that you will see. Pin number 7 is connected to the collector of the NPN transistor internally, that you will see, and pin number 8 is the supply voltage. So this is the pin description of the 555 timer IC. Obviously, when you understand the internal circuitry of 555 timer IC, only then you can understand the functioning of these pins. So coming to the internal circuitry of 555 timer IC. So you can see that this 555 timer IC, it contains 3 5 kilo ohm resistors. That's why it is called 555 timer IC, and it contains 2 comparators. Upper comparator, UC is the upper comparator, LC is lower comparator, and apart from it, there is a SR flip-flop, and there are 2 BJTs. One is PNP transistor, that is Q2, and another one is NPN transistor. This is NPN transistor, that is Q1. So you can see that pin number 1, this is ground pin. Pin number 2 is the trigger pulse, and this trigger pulse is applied at the inverting terminal of the lower comparator. From pin number 3, we take the output. Pin number 4 is the reset pin. Now you can see that this reset pin, pin number 4, is connected to the base of this PNP transistor. So if we want to reset the output, so just we apply the negative pulse, because this is the PNP transistor. Pin number 5 is the control voltage, that is connected to the inverting terminal of the upper comparator. Now see, if we are not applying any voltage, so in that case we just connect a capacitor in between pin number 5 and pin number 1, that is the ground pin, and just to remove the ripples and noise. Pin number 6 is the threshold. This pin number 6, it is connected to the non-inverting terminal of the upper comparator. Pin number 7, you can see this is the discharge pin, and this pin number 7 is connected to the collector terminal of the Q1 transistor, and pin number 8 is the supply voltage VCC. Fine. And in 741 IC, there is also a power amplifier, that is basically the inverter, right? So if we apply 1 at the input of this power amplifier, so we get the output 0. Fine. So now you can understand the working of this 555 timer circuitry. See, this upper comparator and lower comparator, it is in open loop, so obviously the output will be either logic 1 or logic 0. Fine. So the output of the upper comparator will be logic 1 if the voltage at the non-inverting terminal will be greater, right? And the output of the upper comparator will be at logic 0 if the voltage at the inverting terminal is greater. And we know the truth table of SR flip-flop. If S is 1, R is 0, then it is the set state. In this case, the Q will be 1 and Q bar will be 0. If Q bar is 0, so 0 will reach to the input of the power amplifier and the output will be 1. Similarly, in the reset, when the flip-flop is reset, so in that case S will be 0 and R will be 1. In that case, Q bar will be 1 and output will be 0. And this Q1 transistor, that is the NPN transistor, it will be on only when there is a logic 1 at the base of this Q1 transistor. otherwise it will be off. Fine. So this is the description of the individual element inside this 555 timer IC. Now we are going to use this 555 timer IC to design a stable multivibrator. So in a stable multivibrator using 555 timer IC, now see in this circuit we have connected two external resistors RA and RB and one external capacitor C, and I have already explained the internal circuitry of this 555 timer IC. Now you can see that if we are not using pin number 4, that is the reset pin, we have shorted this pin number 4 with pin number 8. That pin number 8 is the supply voltage plus VCC. From pin number 3 we are taking the output. If we are not applying the voltage at the pin number 5, you can see that we have connected a capacitor of 0.01 microfarad in between pin number 5 and pin number 1, that is ground. Since it's a astable multivibrator, so it does not require any input, it does not require any trigger pulse. So in this case we have shorted this pin number 2 with pin number 6, but in monostable multivibrator, since it requires trigger pulse, so we apply that trigger pulse at pin number 2. So this is the circuitry of a stable multivibrator using 555 timer IC. Just to understand the working of this circuit, we need to draw the internal circuit of 555 timer IC, only then we can better understand the working of this stable multivibrator. Now just see this RA and RB, the junction of RA and RB is pin number 7, and this pin number 7 is connected to the collector of Q1 transistor. You can again check it. This pin number 7 is connected to the junction of RA and RB, and this pin number 6 is connected to the junction of RB and C. So this pin number 6 is connected to the junction of RB and C, and this pin number 6, it is connected to the non-inverting terminal of the upper comparator. And since we are not applying any trigger pulse, so this pin number 2 is shorted with the pin number 6. And again we are not applying any voltage at the pin number 5. That's why we have connected a capacitor of value 0.01 microfarad in between pin number 5 and pin number 1, that is the ground pin, just to remove the ripples and noise. Fine. And this pin number 4, that is connected to the base of this Q2 transistor, that Q2 is the PNP transistor. Now see, if you see this circuit, we have not applied any input signal, no trigger pulse, but it still generates output. Fine. So we need to understand that how this circuit generates the output pulse. That pulse contains logic 0 state and logic 1 state. Fine. To understand it, see, when we apply a supply voltage VCC, that VCC, it can be from plus 5 volt to plus 18 volt. Then this capacitor will start charging through this resistor RA and RB. So the time constant will be RA plus RB into C. Now you can see these three resistors of 5 kilo ohm values, it has been connected between VCC and ground. So equal voltage drop will be there across each resistor. So the voltage at this particular terminal, that is the inverting terminal of upper comparator, it will be 2 by 3 VCC, 2 by 3 VCC, because there are 3 resistors. So 1 by 3 VCC voltage drop will be across each resistor. So similarly, the voltage at the non-inverting terminal of the lower comparator, it will be 1 by 3 VCC. Fine. So it means that inside 555 timer IC, the voltage at the inverting terminal of the upper comparator, it is fixed to 2 by 3 VCC, and the voltage at the non-inverting terminal of the lower comparator, it is fixed to 1 by 3 VCC, right? Now when we apply the supply voltage, when we connect supply voltage to this circuit, then this capacitor will start charging. So initially what will happen? The voltage at the inverting terminal of lower comparator, it will be lesser than the non-inverting terminal voltage. So obviously the output of the lower comparator will be 1, and we can see the inverting terminal of the upper comparator, it is at 2 by 3 VCC. So for upper comparator, the voltage at the inverting terminal is greater. So the output of the upper comparator will be 0. Now S equal to 1, R equal to 0 in SR flip flop. So it is a set state. So Q will be 1 and Q bar will be 0. So this 0 will come here, and since this power amplifier it is basically the inverter, so the output will be logic 1. So we will get the high state output, right? Since 0 is at the base of Q1 transistor, since Q1 is NPN transistor, so Q1 will be off, right? So this capacitor will keeps charging and charging with the help of this resistor RA and RB. It means that the capacitor voltage VC, it will increase, and when the capacitor voltage VC, it crosses 2 by 3 VCC. Now you can see that the output of the upper comparator will change from 0 to 1, but in between the output of the lower comparator, it will change from 1 to 0, right? Because when the capacitor voltage, it just crosses 2 by 3 VCC, so the non-inverting terminal voltage of upper comparator will be greater, so the output of upper comparator will be 1. So now it becomes the reset state of flip flop, SR flip flop. It means that now Q bar will be 1. If Q bar is 1, then output will be 0, and if Q bar is 1, then in that case this Q1 transistor will be on. When Q1 transistor is on, then this capacitor will start discharging through this RB resistor and this Q1 transistor, right? So it means that when the flip flop is in reset state and Q bar is 1, then Q1 is on, and when Q1 is on, then capacitor starts discharging through this resistor RB and this transistor Q1. Now capacitor is discharging, it means that the capacitor voltage is decreasing, and when it is decreasing and when it becomes just lower than 1 by 3 VCC, then you can see that the non-inverting terminal voltage of lower comparator, it is at 1 by 3 VCC, and when the capacitor voltage, when it is reduced to below 1 by 3 VCC, then the output of the lower comparator is 1, and obviously at that particular moment the output of the upper comparator will be 0. So again the flip flop will come in set state. In set state, Q will be 1 and Q bar will be 0. If Q bar is 0, so in this case this 0 will come to the input of the power amplifier, that is basically the inverter, and the output will be, now we can again check it. If the output of the lower comparator is 1 and the output of the upper comparator is 0, in this case the flip flop enters in set state, so Q will be 1 and Q bar will be 0. So if Q bar is 0, then the output of the power amplifier, the output of the circuit will be logic 1. So it means that when Q bar is 0, then this Q1 transistor will be off, because 0 will reach at the base of the Q1 transistor. So when Q1 is off, then capacitor will not get discharged. It will again get charged with the help of resistor RA and RB. So in short, we can say that when this Q1 transistor is off, then the capacitor is charging, and capacitor is charging from 1 by 3 VCC to 2 by 3 VCC, right? And when Q1 is on, then capacitor it is getting discharged from 2 by 3 VCC to 1 by 3 VCC, and when the capacitor is in charging state, then the output is high, and when the capacitor is discharging, then the output is low. So this charging and discharging of the capacitor, it continues from 1 by 3 VCC to 2 by 3 VCC, the capacitor is charging, and from 2 by 3 VCC to 1 by 3 VCC, it gets discharged. And whenever capacitor is get charged, then the output is high, otherwise output is low. Now, to understand it better, now you can see that this is the output waveform of this astable multivibrator, and this one is T high and this one is T low. So we need to calculate the frequency of this pulse waveform F0, and the total time it will be T. So F0 will be equal to 1 by T, 1 upon time period. So ultimately we need to find out the value of T high and T low. If we can calculate the value of T high and T low, so just by adding T high and T low we can get the value of T. Once we get time period T, we can calculate F0. So we are going to do the derivation of this F0. We need to calculate the frequency of this output pulse. There we will see that how we can change the frequency of this output pulse. Now see, if we can calculate the time taken by the capacitor to charge from 0 to 2 by 3 VCC, let's say that this time is T1. Now if we can calculate the value, the time taken by the capacitor to charge from 0 to 1 by 3 VCC, let's say this time is T2. So how much time the capacitor will require to charge from 1 by 3 VCC to 2 by 3 VCC? It will be T1 minus T2. And why we are interested to calculate this T1 minus T2? Because when the capacitor is getting charged from 1 by 3 VCC to 2 by 3 VCC, then the output is high. So basically this T1 minus T2 is T high. T1 minus T2 is T high. So from here we can calculate it. We know the capacitor voltage equation VC, that is for this particular circuit VCC 1 minus e to the power minus T by RC. Fine. Where this R is equal to RA plus RB, because the capacitor is getting charged with the help of RA and RB resistor, right? So we need to calculate the time T1. That means the time taken by the capacitor to charge from 0 to 2 by 3 VCC. So this VC will be 2 by 3 VCC is equal to VCC 1 minus e to the power minus T1 by RC. From here we can calculate the value of T1. That is equation number 1. Similarly we can calculate the time taken by the capacitor to charge from 0 to 1 by 3 VCC. That will be 1 by 3 VCC is equal to VCC 1 minus e to the power minus T2 by RC. So from here we can calculate the value of T2, equation number 2. So from equation number 1 and equation number 2, we can calculate the value of T1 minus T2, that is T high, time during which the output is high. So after calculation you will get 0.69. You can do this calculation, 0.69 RA plus RB into C. Basically that R is equal to RA plus RB, because the capacitor is getting charged with the help of resistor RA and RB. So we have calculated the time T high. So we need to calculate the value of T low now. Now we know that the output is low when the capacitor is getting discharged from 2 by 3 VCC to 1 by 3 VCC. So the equation is, the final value is 1 by 3 VCC, that is equal to 2 by 3 VCC, 2 by 3 VCC into e to the power minus T by RC, where this T is basically T low. Fine. And we have seen that the capacitor is getting discharged with the help of resistor RB only. Come to the circuit, you can see that this capacitor is getting discharged with the help of this resistor RB only. There is no RA involved in it, because when this Q1 transistor is on, then capacitor is getting discharged with the help of RB and this Q1 transistor. So from here we can calculate the value of T, that T is T low, and after calculation you will get 0.69 RB into C, where R is equal to RB, because in the discharging path only one register is coming, that register is RB. So we have calculated the value of T high and T low. From here we can get the value of T, that T is equal to T high plus T low, and this T is equal to time period. Fine. So it will be 0.69 RA plus T into C. This is the time period of the pulse waveform generated by the stable multivibrator. So the frequency F0 will be equal to 1 by T. So you can calculate it. After calculation you will get 1.45 upon RA plus 2 RB into C. So this is the frequency of the output pulse. Now just by changing the value of RA and RB and C, we can change the frequency of the output pulse. Now we can calculate the duty cycle also from here. Duty cycle D, it is normally expressed in percentage. It is defined as the time duration for which the output is high upon total time T into 100. Fine. So T high we have calculated, that is 0.69 RA plus RB into C upon total time T is 0.69 RA plus 2 RB into C into 100. So it will be cancel out. So the duty cycle is RA plus RB upon RA plus 2 RB into 100. Now we know that for square wave the duty cycle is 50%. So to make the duty cycle 50%, you can see that if in this equation we put RA is equal to 0, then the duty cycle will be 50%. But we don't do that because it is very dangerous. Why it is dangerous? The reason is, if we put this RA register equal to 0, it means that we are shorting this pin number 7 to pin number 8 directly, and this pin number 7 is connected to the collector of this Q1 transistor, So if we put RA equal to 0, in that case the collector of Q1 transistor will be directly connected to the supply voltage, and this Q1 transistor may get damaged and your timer IC will get destroyed. Fine. So we don't do that. To make the duty cycle 50%, we don't make RA equal to 0. That is not good. So to make the duty cycle 50%, to get the symmetrical square wave, what we do, one thing we can do just by using diode and variable resistor. Another method is to use JK flip flop. For that, what we do, coming to this circuit again, see, we have understood how this astable multivibrator is generating this pulse waveform, but the duty cycle of this pulse waveform is not 50%, and we want this 50% duty cycle. Fine. For that, we use a JK flip flop, and in JK flip flop we short J and K, and we connect this J and K to plus VCC. It means that J and K both are 1, and the output of a stable multivibrator, it acts as a clock pulse for the JK flip flop, and this is the output Q and Q bar. Let's consider positive edge triggered JK flip flop. Fine. So what we are doing, to get the 50% duty cycle, we have connected the output of this circuit to the clock of the JK flip flop, and we have made this J equal to K equal to 1, and we know that when J equal to K equal to 1, then the output toggles. By doing this, we can get the symmetrical square wave. That means the duty cycle will be 50%. So to understand it, now see, the output of the astable multivibrator is this one. Fine. And if we mark the positive edge, let's consider positive edge triggered JK flip flop. So this one is the positive edge, right, low to high. Then this one is the positive edge, positive edge, positive edge. So in JK flip flop, when J and K both are 1, then the output toggles. Fine. So the output of the JK flip flop, that is Q. It means that when the first clock comes, then the output will toggle from 0 to 1, and When the second clock comes, then the output will toggle from 1 to 0. When the third clock comes, then output again toggles. So the same thing happens. So you can see that the output of the JK flip-flop, that is Q, we get a square wave whose duty cycle is 50%. So this is one of the method to get the 50% duty cycle just by connecting a JK flip-flop at the output of the Astable multivibrator. But the output should be connected to the clock. The output of the Astable multivibrator will act as a clock for JK flip-flop. Fine. Now coming to the applications of Astable multivibrator using 555 timer IC. So one of the application is square wave oscillator, that we have seen that we can generate 50% duty cycle pulse waveform with the help of Astable multivibrator. And the another application is FSK generator, pulse position modulator. So in this class I have discussed the pin diagram of 555 timer IC, what is 555 timer, internal structure, internal circuitry of 555 timer IC. Then I have discussed the Astable multivibrator using 555 timer IC and its derivation. Then we have derived the frequency of the output pulse and duty cycle. Then I have discussed that how we can get 50% duty cycle just by using JK flip-flop, followed by applications of Astable multivibrator. These are the references. Thank you.